Hey guys, it's Greg. Uh, I'm gonna do this one tonight. It's this part here is just an introduction to the video. When Matt and I are usually talking on the phone, we talk a lot about the probability of things. Um, it's amazing and actually kind of ridiculous that people, and I'm not talking about you and me and anybody that would be watching this. I'm talking about the masses. When you start saying that this is a million to one shot, and that's a million to one, and this is a million to one, and that's a million, when you start adding all of that stuff up, it becomes an impossibility. And people don't they don't seem to realize that, and they I don't even think they even consider it or care. Um, but somewhere you've got to override this bullshit that they've put into you with common sense and logic that when you get to the law of probability. And I'm going to put in the short version here of um, Dr. Albert Bartlett's lecture on the exponential function. It's about 10 minutes long. It's worth the watch. The video on it's not that good. Uh, there is a longer version. It's on here, I'm sure. I think it's titled "The Most Important Video You'll Ever See," something like that. But I'm gonna just tack the shorter version on. It just goes to show the exponential function and how improbable this stuff really is. If you need something, something to fire back at these people with, as far as the SpaceX shit and or the taking 3 rounds in the chest using a bump stock. I mean, that had to be a mounted gun. It had to be. You can't, if that, based on trajectory, if that barrel had moved even a centimeter or whatnot, it's going to wind up at that distance 10, 15, 20 feet off. Can't hit somebody 3 times in the chest with a bump stock. That's just uh, people don't. I don't think people. The law of probability. The people don't understand how to figure out statistically what's possible, what's not. So I'm just going to include this. Tack it on to the back of this right quick, and I'll leave it at that. And if you want to watch the entire lecture, just look for Exponential Function, Dr. Albert Bartlett. I think it's titled something like one of the most important videos you'll ever see. Anyway, that's it for now. I'm going to tack it on right here and go ahead and watch it. It's about 10 minutes long, and maybe it'll give you something to use. Okay, so until next time, have a good one, and please be good to everyone else.
Well, it's a real pleasure to be here and to have a chance just to meet with you and talk about some of the problems that we're facing. Now, some of these problems are local, some are national, some are global, but they're all tied together. They're tied together with arithmetic, and the arithmetic isn't very difficult. And what I hope to do is I hope to be able to convince you that the greatest shortcoming of the human race is our inability to understand the exponential function. So you say, well, what's the exponential function? This is a mathematical function that you would write down if you're going to describe the size of anything that was growing steadily. If you had something growing 5% per year, you'd write the exponential function to show how large that growing quantity was year after year. And so we're talking about a situation where the time that's required for the growing quantity to increase by a fixed fraction is a constant. 5% per year, the 5% is a fixed fraction, the per year is a fixed length of time. Now that's what we want to talk about. It's ordinary, steady growth. Well, if it takes a fixed length of time to grow 5%, it follows it takes a longer fixed length of time to grow 100%. Now that longer time is called a doubling time. We need to know how you calculate the doubling time, and it's easy. You just take the number 70, divide it by the percent growth per unit time, and that gives you the doubling time. So our example of 5% per year, you divide the 5 into 70, you find that growing quantity will double in size every 14 years. Well, you might ask, where did the 70 come from? The answer is it's approximately 100 multiplied by the natural logarithm of 2. If you wanted the time to triple, you'd use the natural logarithm of 3. So it's all very logical. But you don't have to remember where it came from if you'll just remember 70. Now, I wish we could get every person to make this mental calculation every time we see a percent growth rate of anything in a news story. For example, if you saw a story that said things have been growing 7% per year for several recent years, you wouldn't bat an eyelash. But when you see a headline that says crime has doubled in a decade, you say, my heavens, what's happening? Well, what is happening? 7% growth per year. Divide the 7 into 70, the doubling time is 10 years. But notice, if you're going to write a headline, you never write crime growing 7% per year, because most people wouldn't know what it really means. Now, do you know what 7% really means? Let's take another example from Colorado. The cost of an all-day lift ticket to ski at Vail has been growing about 7% per year ever since Vail first opened in 1963, and at that time you paid $5 for an all-day lift ticket. Now, what's the doubling time for 7% growth? 10 years. So what was the cost 10 years later in 1973? 10 years later in 1983? 10 years later in 1993? And what do we have to look forward to? Now, this is what 7% means. Most people don't have a clue. Well, let's look at a generic graph of something that's growing steadily. After one doubling time, the growing quantity is up to twice its initial size. 2 doubling times, it's up to 4 times its initial size. Then it goes to 8, 16, 32, 64, 128, 256, 512. In just 10 doubling times, it's 1,000 times larger than when it started. And you can see, if you tried to make a graph of that on ordinary graph paper, the graph will go right through the ceiling. Now let me give you an example to show the enormous numbers you get with just a modest number of doublings. Legend has it that the game of chess was invented by a mathematician who worked for a king. The king was very pleased. He said, I want to reward you. And the mathematician said, my needs are modest. Please take my new chessboard and on the first square place 1 grain of wheat. On the next square double a 1 to make 2. On the next square double a 2 to make 4. Just keep doubling till you've doubled for every square. That will be an adequate payment. Well, we can guess the king thought, this foolish man. I was ready to give him a real reward. All he asked for is just a few grains of wheat. Well, let's see what's involved in this. We note there are 8 grains on the 4th square. Now, I can get this number 8 by multiplying 3 2's together. It's 2 times 2 times 2. It's 1 2 less than the number of the square. Now, that follows in each case. So, on the last square, I'd find the number of grains by multiplying 63 2's together. Now let's look at the way the totals build up. When we have 1 grain on the first square, the total on the board is 1. We add 2 grains, that makes a total 3. We put on 4 grains, now the total is 7. 7 is a grain less than 8. It's a grain less than 3 2's multiplied together. 15 is a grain less than 4 2's multiplied together. Well, that continues in each case. So when we're done, the total number of grains will be 1 grain less than the number I get multiplying 64 2's together. And my question is, how much wheat is that? You know, would that be a nice pile here in the studio? Would it fill the building? Would it cover the county to a depth of 2 meters? How much wheat are we talking about? The answer is it's roughly 400 times the 1990 worldwide harvest of wheat. Now that could be more wheat than humans have harvested in the entire history of the earth. You say, how'd you get such a big number? It was simple. We just started with one grain, but we let the number grow steadily till it had doubled a mere 63 times. There's something else that's very important. The growth in any doubling time is greater than the total of all of the preceding growth. For example, when we put 8 grains on the 4th square, the 8 is larger than the total of 7 that were already there. When we put 32 grains on the 6th square, the 32 is larger than the total of 31 that were already there. Every time the growing quantity doubles, it takes more than all that you'd used in all of the preceding growth. Now, let's translate that into the energy crisis. Here's an ad from the year 1975, and it asks the question, could America run out of electricity? America depends on electricity. Our need for electricity actually doubles every 10 or 12 years. That's an accurate reflection of a very long history of steady growth of the electric industry in this country, growth at a rate of around 7% per year, which goes with doubling every 10 years. Now, with all that history of growth, they expected the growth would just go on forever. Fortunately, it stopped. Not because anyone understood the arithmetic, it stopped for other reasons. But let's ask, what if? Suppose the growth had continued. Then we would see here the thing that we just saw on the chessboard. In the 10 years following the appearance of this ad, in that decade, the amount of electrical energy that we would have consumed in this country would have been greater than the total of all of the electrical energy we had ever consumed in the entire preceding history of the steady growth of that industry in this country. Now, did you realize that anything as completely acceptable as 7% growth per year could give such an incredible consequence that in just 10 years you'd use more than the total of all that had been used in all of preceding history? Well, that's exactly what President Carter was referring to in his famous speech on energy. One of his statements was this. He said, and in each of those decades, more oil was consumed than in all of mankind's previous history. Now, by itself, that's a stunning statement. Now you can understand it. The president was telling us a simple consequence of the arithmetic of 7% growth each year in world oil consumption, and that was the historic figure up until the 1970s. Now there's another beautiful consequence of this arithmetic. If you take 70 years as a period of time, and note that that's roughly one human lifetime, then any percent growth continued steadily for 70 years gives you an overall increase by a factor that's very easy to calculate. For example, 4% per year, you find the factor by multiplying 4 2's together. It's a factor of 16. Now, a few years ago, one of the newspapers here in Boulder quizzed the 9 members of the Boulder City Council and asked them, what rate of growth of Boulder's population do you think it would be good to have in the coming years? Now, the 9 members of the Boulder City Council gave answers ranging from a low of 1% per year. Now, that happens to match the present rate of growth of the population of the United States. We are not at zero population growth. Right now, the number of Americans is increasing by more than 3 million people every year. No member of the City Council said Boulder should grow less rapidly than the United States is growing. Now, the highest answer any council member gave was 5% per year. Well, you know, I felt compelled. I had to write them a letter and say, did you know that 5% growth for just 70, I can remember when 70 years used to seem like an awful long time. It doesn't seem so long now. Well, that means Boulder's population would increase by a factor of 32. That is where today we have one overloaded sewer treatment plant. In 70 years, we need 32 overloaded sewer treatment plants. Now, did you realize that anything as completely all-American as 5% growth per year could give such an incredible consequence in such a modest period of time? Our city council people had zero understanding of this very simple arithmetic. In the summer of 1986, the news reports indicated that the world population had reached the number 5 billion people, growing at the rate of 1.7% per year. Well, your reaction to 1.7 might be to say, that's so small. Nothing bad could ever happen at 1.7% per year. So you calculate the doubling time, you find it's only 41 years. More recently, in 1999, we read that the world population had increased from 5 billion to 6 billion people. The good news is that the growth rate had dropped from 1.7% per year to 1.3% per year. The bad news is that in spite of the drop in the growth rate, the world population today is increasing by something over 80 million people every year.